Dear students, this is Dr. Anima Upadhyay and today we will be discussing about the bomb calorimeter and the determination of calorific value using bomb calorimeter. In the previous lectures, we have discussed about the calorific value and its types. For determining the calorific value for solid and non-volatile liquids, we use bomb calorimeter. But if we want to determine the calorific value of gaseous fuels or a volatile liquid fuel, then we have to use another apparatus called the Boy's gas calorimeter and not the bomb calorimeter. So let us now start the discussion about the bomb calorimeter. So as I have said that the solid and non-volatile liquids, if their calorific value we have to determine, we'll use the bomb calorimeter. And for gaseous and volatile liquid, Boy's gas calorimeter is employed to determine the calorific value. This is a bomb calorimeter. The figure looks very complicated and one can be puzzled how to draw this diagram. So this is not as complicated as you are thinking. If we start from the center, that is the bomb. This is the bomb. This bomb is made up of stainless steel, which is non-corrosive in nature. And you can see there are two electrodes. These two electrodes are made up of stainless steel. To one of the electrodes, a ring is fitted. This ring is used to hold the crucible. The crucible is made up of nickel or stainless steel. Both the electrodes are connected with a 6 volts battery and a magnesium wire is stretched between the two electrodes to burn the sample whose calorific value is to be determined, and it is taken in the crucible. The bomb is then closed with the help of a ebonite lid which is provided with an inlet valve for the oxygen. The oxygen is allowed inside only that much, which is just sufficient to burn the fuel sample whose calorific value we are going to determine. Now this bomb is placed in a copper calorimeter. In the copper calorimeter, a known mass of water is taken and it is provided with an electrically operated stirrer and Bachmann's thermometer. This is very important. We should always take a Bachmann's thermometer in the copper calorimeter and no other thermometer. This entire device is then surrounded by an air jacket and then with a water jacket, and then it is sealed with a lid made up of ebonite so that there should not be any losses of heat due to conduction, convection or radiation. So now you can see it is very easy to draw the figure of a bomb calorimeter, starting from the bomb making the two electrodes and a loop to hold the crucible, magnesium wire stretching between the two electrodes connected to a 6 volts battery, an inlet valve in the ebonite lid, then copper calorimeter filled with the water and electrically operated stirrer, Bachmann's thermometer, followed by air jacket, then water jacket. Next is the principle. So the bomb calorimeter is based on a simple principle of heat lost is equal to heat gained. So the fuel which we have burnt liberates the heat and the water taken in the calorimeter absorbs that heat. This is the principle of bomb calorimeter. Construction I have already explained to you, and this is what is written here, that the bomb is made up of non-corrosive stainless steel fitted with two stainless steel electrodes, and the electrodes are connected to a 6 volts battery. A ring is attached to the electrodes, one of the electrodes to hold the crucible in which the fuel sample is taken. A magnesium wire is there to burn the fuel which is taken to determine the calorific value. Bomb is closed with an ebonite lid provided with an inlet valve for oxygen. Placed in a copper calorimeter in which a known mass of water is taken, provided with an electrical stirrer and a backman's thermometer. The entire device is then surrounded by air and water jackets. Working of a bomb calorimeter. How it works? So first thing is we have to take the fuel sample whose calorific value we are going to determine. It is taken and crushed into very small pieces. Approximately 0.5 to 1 gram of sample is taken in the crucible. The fuse wire is then stretched properly and the lid of the bomb is screwed down. Oxygen is taken around 25 to 30 atmospheres. Then the bomb is lowered in the copper calorimeter, in which we have already taken a known mass of water. The initial temperature of the water is noted down using the backman's thermometer. The electrodes are then connected with the 6 volts battery and the fuel is burnt. On burning the sample, it liberates heat which is absorbed by the water taken in the copper calorimeter. The water in the calorimeter is continuously stirred and the rise in the temperature when it becomes constant is recorded with the backman's thermometer again, and all the observations are recorded to calculate the higher and the lower calorific value. So how to record the observations? Whenever we perform an experiment, the observations are always recorded. So first thing is the mass of the fuel that we have taken. Suppose it is small a in grams. The mass of water which we have taken the calorimeter is suppose capital W in grams. The water equivalent of calorimeter, stirrer, thermometer, bomb, etc. is suppose small w in grams. The initial temperature of the water in the calorimeter is recorded. Say it is T1 degree centigrade. Final temperature of the water in the calorimeter which is recorded. Say it is T2 degree centigrade. And the higher calorific value which we are going to calculate, suppose it is capital G in calories per gram. Then how will do the calculations? We know from the principle that heat liberated by the fuel is equal to the heat absorbed by the water and the apparatus. Suppose the heat liberated by the fuel is small a into capital G, where G is the higher calorific value which we are going to determine, and small a is the mass of the fuel taken in the crucible. Heat absorbed by the water in the calorimeter and apparatus is W plus small w into T2 minus T1. Then higher calorific value, that is HCV, can be calculated using the formula capital G is equal to capital W plus small w into T2 minus T1 divided by A calories per gram. Once we have calculated the capital G, we can calculate the LCV using the formula LCV is equal to HCV minus latent heat of water vapor formed. That is G minus 0.09 H into 587 calories per gram. Here H is the percentage of hydrogen present in the fuel and the latent heat of steam is 587 calories per gram. So whenever you are solving a numerical, the percentage of hydrogen is given and the latent heat of steam is also given. In this way, substituting all the values, we can calculate HCV and LCV. Sometimes we go further into the calculations to make more precise and more accurate results. For that, we need to take into consideration certain corrections, that is acid correction, fuse wire correction and cooling correction. Now acid correction is denoted by TA. The fuels which contain sulfur and nitrogen, on burning they get converted into their respective acids, and during this the heat is liberated because these reactions are exothermic. But this does not add to the calorific value of the fuel. Therefore, they are of no use. Hence, it should be subtracted. Similarly, the fuse wire correction, TF, it is the amount of heat equivalent in calories which is produced on burning the fuse wire. This heat is also not added to the calorific value of the fuse. Therefore, it should also be subtracted. But the cooling correction TC is the time taken to cool the water in the calorimeter from maximum temperature attained to the room temperature, and it adds to the calorific value. Therefore, we will add it to the difference in the temperature. On applying these corrections, the formula for calculating the higher calorific value, that is G, is capital W plus a small w into T2 minus T1, that is the change in the temperature, plus Tc, that is the cooling correction, minus Ta plus Tf divided by A in calories per gram, where Ta is acid correction and Tf is fuse wire correction. So this is how we can calculate the higher calorific value and lower calorific value from the formula using Bomb Calorimeter. Thank you.